So who better than to start us off talking about risk than one of the pioneers in this field in equilibrium, Yves Smeers, from Université Louvain, and he's done a lot of work, fundamental work in this area with some of the other people in the room, Danny Ralph and Gautier and Anthony, and he's going to tell us in the first talk about risk-free and stochastic equilibrium. Very much looking forward to it.
Okay, thank you. At least I will try to give the talk. I don't feel very well since I'm here, and I may have problems, but I have a backup who can pick up the talk if I have a problem. So the first thing is about the introduction, why we are working on that. The thing came from a very practical problem. So there is a company which is mentioned there, and at some point the company moved outside of its home country, let's say, to other places and wanted to invest in other places. No, they didn't want to invest the whole utility, so they were looking in terms of project development. And then they got some discount rate from investment banks that were different depending on the technology and on the country. And then there's the question, well, we have that standard capacity expansion model. That capacity expansion model has just one discount rate. What should we do when we have several discount rates? That was the origin of the thing. So I will go through different versions of that discount rate. And in fact, this introduction on the differentiated discount rate, in fact, they are justified because in different places for different technology in the energy transition, the plants are exposed to different risks. And if the plants are exposed to different risks, and if you just think in terms of a capital asset pricing model, well, they should have different discount rates. And so it's something very natural to try to insert those differentiated discount rates in the capacity expansion model. Okay, well, the tradition has been to have a single discount rate both in generation and in transmission. That discount rate came from the regulation. The regulation still applies to the transmission, but it does no longer apply to generation. And in fact, because you have competition between different companies, those different companies can have different risk exposures and hence different discount rates. And if they invest by project, then each of the project can have a different discount rate. And so the question is to see what we can do with the requirement that we need to have different discount rate in capacity expansion models. Well, I will start with something which is essentially what is used everywhere, both in the regulated sector and in the competitive sector, namely the capital asset pricing model that gives the cost of equities for a project or for a company which is exposed to different risks. The tradition is that people use that, at least they claim to use that. It's not always easy to use it, but in fact the principle, or at least the hidden methodology, is the capital asset pricing model, and I will work on that. There is also another part of the risk, which is the cost of the bonds, but that can be modeled too, but that's a different problem. In fact, one may say this is a tiny problem, there is no need to look at that, but that's not true. I just took as an example because, well, we are in the UK, that DEC has conducted several studies on the use of different discount rates for different technologies, and in fact, that it found that it was not very easy to handle. They have resorted to NERA to look at those things, and there are some interesting discussion between what NERA produced and some comment of Derek Bunn showing that this is not an easy problem. So the justification for the different discount rate is that in fact you have different risk exposures. It doesn't mean that it's easy to do. When you look at the stock market and the risk factors, well, they've been looking at some good models for those things, and there is some literature on the fact that it's difficult to identify what should be the good risk factors. So Cochrane talks about a zoo of possible discount rate without one being able to assert risk factors, to one being able to assert which one to use. Okay, now we'll start with the CAPM, where the market is the reference discount rate, so that means well, the set of all the equities, let's say. This thing is commonly used, but there are issues. So there is something which has been long-lasting, which is the equity premium puzzle. So the amount of risk premium that is there. There is a singular argument in the thing, namely that when you invest, you use the discount factor, but the discount factor changes your investment, and when you change your investment, you change the risk exposures, and hence you should. So in fact, it's a fixed point problem, but it is never treated as a fixed point problem. There is also the fact that when you rely on that model, you essentially use the past or the past correlation, while you need normally to take into account future correlation. So in this paper, we are not looking at the theory beside the discount rate, because this is for economists, but we try to see what we can do, given that some people give different things about discount rate, to embed them in computable models. I will skip this one, which is a little bit difficult, but in fact it says that that's a result of the simulation that we have, that when we put the risk factor in the model, and depending on how you measure that risk factor, in fact we calibrate the risk factor with respect to a market data, which is a Sharpe ratio of the market, and you can find in the welfare of the different agents amounts which are of similar magnitude as those that you find when you reduce CO2. Okay, when you reduce CO2, you have real cost, that's for sure. Now, when you look at the welfare coming from risk factors, you have something that really results from what you have put in the risk functions or in your measure of the risk, and so this is not as objective as real cost. But in fact, the amount that you can find are significant. Also, something which is interesting is that these amounts come from the fact that when you have the discount, when you hedge your risk in those models, when you have introduced hedging in those models, in fact, you change the discount rate, and that was already pointed out in those studies that were done for DEC, namely that, well, there is the traditional approach to the discount rate, but one should take also into account how they would be adapted depending on whether you introduce hedging for the plans or not. So I will start with something which might be surprising, but which is that the traditional method for dealing, or at least if you deal very simply with the different discount rates in a capacity expansion model, then you may get some strange behavior. I'll start with the model will be simple. This one is dynamic because I needed to show the arbitrage problem that occurs, but in fact it is very simple. So we have different projects, and you invest in T and you operate those projects for some horizon. You have some fuel cost, you have some overnight investment cost, and you have demand, and you have a discount rate that is specific to the project. A discount factor that is specific to the project. Alpha K is the project, which is 1 divided by 1 plus the discount rate. And you have to deal with those different discount rates. Then you start with the standard investment criterion. That one cannot say that that's theory, that's the basic thing. So let's assume that you have some electricity price, pi of t, from 1 to t, that you have some variable that represent the plant operation, and you invest if the discount revenue at the discount rate of the plant is greater than the overnight investment cost. So this is for one plant, and that's a criterion that you can extend to different plants. So this is the extension where you have different plans for an agent K, and then each agent K optimizes its portfolio in exactly the same way. Then the problem assumes that you can foresee the price, and in order to complete the thing, you need a market to specify the price. So if you have that maximization, that's an optimization of an agent. You have several agents, so you have optimization, individual optimization of several agents, and that's very close to a Nash problem. And in fact, it becomes a Nash problem if you add that market clearing price. Now, we put this thing in complementary form because we want to show something that may look a little bit strange. The first relation will give you the price pi as a function of mu, which is the marginal value of the plant, and the cost, the operating cost of the plant. So that just says that the price pi is equal to the marginal is equal to the marginal cost of the plant plus the marginal value of the plant. Then you have an investment criterion that takes into account the differentiated discount rate of the different agents. You have that in the alpha, which is on top of the operating overnight investment cost. And then you have the standard thing that says that you cannot operate a plant more than the existing capacity of the plant. Then you have a market clearing condition, and the thing which is maybe a little bit particular in that problem is that each operator has its own discount factor, because that's the requirement that is posed for that problem. Okay, now you can see that problem in deterministic form or in stochastic form. If it is a deterministic model, well, we just have a scenario. If it is a stochastic model, then you have an even tree of scenario, and you have exogenous processes, namely the operating cost, the investment cost, and you have endogenous processes, namely the prices coming from the system. So the thing is that this problem, if you are not careful, introduces an arbitrage, an internal arbitrage. This is something that you typically don't like to have in a model. So let's assume the typical situation of, let's say, the asset pricing theory, where you would have different risk factors, and each of the you want to work with the discount factor of each of those risk factors. So you might say that electricity is driven by its own risk factors. Fuel cost is driven by its own factors. Those are not exposed to the same risk. So you might have different discount rate for electricity and different discount rate for the other factors. That is something that you can find, in fact, by applying existing theory that you find in textbook. No, we simplify the thing by saying that we have, in fact, two risk factors. One that applies to electricity, to the endogenous process, and then risk factors to apply to the exogenous risk factors. So the thing is that you can transform your fuel cost using the discount rate of fuel cost, because those are exogenous. In contrast, you cannot do the same transformation for the electricity price. So, if you do that, and if you rewrite the problem, you have these relations. The first one determines the price of electricity in time t. So it's the preceding version that determines the price of electricity as a function of the cost of the operating cost and the marginal value of the plant, which is mu. And you apply the discount rate on that one because you want to introduce the discount rate corresponding associated to electricity in that relation. Now, the interesting thing is that each operator sees a different present value of the price of electricity in the future. So if you write all those standard equations and you apply the discount rate of each of those standard equations for the formulation of the price, when the investor sees the price in times t and brings it back to time 0, it uses the discount rate of electricity that it has. And the rest remains as such. On the other hand, you have, when you look at the market clearing, just a single relation. So that means you have different prices you have as many prices of electricity as you have investors, plus one, the one of the market clearing problem, and the one of these investments. So this is a situation where you have different prices of electricity. This violates the law of the single price, and so this is something that typically you don't like to have, especially if you deal with a commodity which is tradable, in this case electricity. Now, if you want to think in terms of the more mathematical version of the thing, this looks like a generalized Nash equilibrium where you try to find several several dual variables for the constraint, for the market clearing constraint. Each of those dual variables is associated to a particular agent. And typically this is not what you like to have in a model for an investor. He doesn't like to see different prices, different possible price of electricity. But the main concern when we look at the problem like that is to have typically, when we build a model, an arbitrage in the model. So this is a standard model. So that means that it doesn't create that kind of problem where you just when you just work with a single discount factor. But this thing occurs as soon as you say those different agents or those different plans have different discount factors, and we want to apply them to the model. Obviously, we want to get rid of them. So the example is taken to show the problem just on the electricity price, because this is typical of an arbitrage in a forward market, something that you want to exclude. So we should have one price for each tradable commodity. Now, if you look at capacity, this is not typically a tradable commodity. So you might have different risk of capital for different plans, because the argument against the arbitrage for those plans does not apply. So in the rest, we will just look at different cost of capital for the investment for the different plans. So I will now simplify the thing and take a static model just to get rid of unnecessary notation. So I drop the time index, but I consider an omega that represents different states of the world. I only have one index for a typical plant, K. Then I now introduce different discount rate. I introduce alpha K of omega, which I call the stochastic discount factor, but that's a typical expression in the thing. It will come later, which is the discount factor for state of the world omega seen by agent K. You would say, why are they different discount factors? Well, because people we want to represent those different discount factors because we are asked to represent those different discount factors. We cannot tell the people who pose the problem, look, this is stupid, so no, we have to work with it. I work with annualized discount investment costs, which are discounted at the risk-free rate, and all the rest is in the alpha. Then mu is the marginal value of the plant, so this is typically the dual variable associated to the relation between the operating variable and the capacity. I take the expectation of those alpha, which is the expected discount marginal plant of the expected discounted value of the plant. This is typically the criterion that you use, that you compare to the investment cost to invest. So typically, if the expected value at your discount rate of the plant is equal to the investment cost, you invest. That's the criterion. And so that means that I change the probability of the investment criterion for each agent, which is something that you do in contingent prices. So I have then the expectation, the next to last line, the expectation of alpha K mu, expected discount marginal rent of the plant K. This is what I compare to the investment cost. And then I introduce a risk premium. I look at what is the expected value of that plant, taking into account the fact that it has a special discount rate, minus what the expectation of the plant would be if all were working at the risk-free rate. And that discount factor is specific to the agent and can be specific to the plant. So when we do that, we respond to the request. Namely, we can have a discount premium that differs from the risk-free rate, and that applies for dealing with country risk or for technology risk. I rewrite my complementary problem. Now I have a producer problem, which is the standard KKT condition of a very simple capacity investment problem. And the capacity expansion problem doesn't have to be simple, but in fact this thing is easy to remember. The first relation and the relation that sets the price seen by the agent as a function of its fuel cost and the marginal value of the plant. The second one is the investment criterion, taking into account the differentiated discount factor. So I take now the expectation on P, well, the standard the statistical probability of mu, but using the stochastic discount factor alpha k, which is in fact the premium that has to correspond somewhere to the stochastic, to the discount to the risk premium that this investment bank mentioned. So EP of alpha k of mu corresponds to includes that differentiated discount factor, that differentiated risk that the investment bank wants to invest to put in the model. And then I have the standard. The third one is a standard equation that says that the operating cost, the operating variable cannot exceed the capacity variable, and which has as a dual variable the mu k. Now the mu k is multiplied by the expectation of the stochastic discount rate, and then contains the risk premium that you have on the problem. I introduce a consumer problem, so to have the usual Nash representation, and a market clearing problem. Now, I want to separate, to identify and to give some special treatment to the premium. So this is exactly the same relation as before, except that in the second relation, that has the expectation on P of alpha k of mu, of alpha k times mu, I decompose it into the risk premium itself, which is the expectation on P of the alpha k minus the expectation on the alpha, which is the risk-free rate. That's the premium, and I use the risk-free, and I use plus the expectation of the risk-free rate. So this is exactly This is exactly the total value of the plan, the marginal value of the plan, except that I have separated it in two things. One which is the one at the risk-free rate, and the other one which is the risk premium. I write the market clearing, and I say let's assemble all those risk premium into something, and I can rewrite my complexity problem in this form, the solution of a generalized equation, where I have some mapping AZ that correspond to the, that correspond to the standard KKT conditions, so everything at the risk-free rate, plus a mapping that contains the risk premium, and then the normal cone to have the non-negative relations. Okay, this suggests problem splitting, and also this introduces, at least this put separately in some block, the B of Z, where I want to introduce different models of risk premium. So in terms of the interpretation, this is not a monotone problem. A of Z plus the normal cone is the monotone problem. That's the KKT condition of the standard capacity expansion problem. This one is very simple, but you can make it more complicated. It is monotone, but it's not strictly monotone. But if you write a complete market, if you instead of working with the risk-free rate, you work with a complete market, then you typically introduce something which is convex. You introduce something which is strictly convex, or which can be strictly convex, and then a perturbation, not a Tikhonov perturbation, standard one, but okay, one where you perturb the risk premium to move to a risky market. The problem where you perturb so as to make the market risky but complete. So then you get something which is indeed strictly convex. Now, well, Yongxi probably knows what to do when you have copositive, but I don't know. So the whole problem is copositive; it is not monotone. And then the question is to deal with that. So there are no, we now look at the discount factor, the stochastic discount factors. It should not be discount rate, it should be stochastic discount factor. They are linear and non-linear. So the first one is the one that everyone uses, whether noticing that with the interpretation or without interpretation, the capital asset pricing model. Well, the thing is extremely developed in finance with a lot of pro and positive and negative comments. In fact, it remains a controversial subject. Now, when we discuss with the people from the company asking why do you apply that in capital budgeting, well, we do what everybody else is doing, so we do it by analogy. Well, then we discussed a little bit more, and the people asked to change department because the discussion wasn't bearable. And the thing which is important is that calibration of historical data. And for instance, one sees in all those papers that were produced by NERA for DEC and also that we should try to get some foresight of correlation at least, and one should move away from just working with purely historical data. Then there are many additional considerations because one knows that while the theory is there, it does not necessarily contains everything. And then there is an extension discussion of whether you have to work with a static CAPM or a conditional CAPM. Okay, so that means that it's a controversial subject. I don't get into that. But while it is presented as something that doesn't cause any problem, it causes problem. So we can do two things. We can work what everybody does and work with the deterministic optimization problem. So that means that you set in B of Z the difference between the discount factor applying to the technology or to the plant minus the risk factor. And so when we do that, we end up with a model that contains arbitrage. The complementary problem is not monotone. In fact, this difference between the plant discount factor and the risk-free rate destroys the monotonicity of the thing. You only use the ex-ante correlation, and you between the plant revenue and the market, and you transpose them in the future. Now, what is funny is that when you don't want to work with the deterministic model, and then when you use the exact definition, or when you use the definition of the stochastic discount rate, that I will elaborate a little bit afterwards, all those non-monotonicity problem disappears. You have a stochastic problem which is convex, which is a convex set of solutions, and which has everything nice. But there is a cost to that. That means that when you draw your scenarios, you need to have the market, because you need in your stochastic model to be able to represent the correlation between the mu, the revenue of the plants, and the market, the evolution. So you need in those scenarios a tree, in the trees, some evolution of the market. You calibrate the stochastic discount factor ex ante, so that's still a drawback. But on the other hand, what you get from the result is a new correlation between the revenue of the plant and the market. So even though you have calibrated your stochastic discount factor on the basis of the past, as in the standard model, you relax that condition when you move to the use of the model. Okay, now how do you do that? Well, you define the stochastic discount factor in a very simple way. So in fact, the CAPM prices two things. It prices the market, and it prices the risk-free asset. So you write alpha omega as A minus B times R, the return of the market, and then you say here that the expectation of your alpha is the risk-free discount factor, and the expectation of the return of the market is also the risk-free discount factor. So that means that you have a change of probability, the alpha omega, which applies to each of the states of the world, and you multiply the natural probability, the P, by the alpha omega. So you make the same kind of thing that when you do in finance, except that the alpha is given by those things, and you do the expectation in that different probability. So that has been extended, and there are more general discount factors. Well, in the interest of time, I am not going to elaborate on that, but in fact, there is an alternative theory that says, well, we should take a different discount factor, but the principle of the theory are the same. You introduce a stochastic discount factor that has to price all those risk factors that are priced by the market and the risk-free rate. So this says that I'm looking for risk factors that the market will price, and I want my stochastic discount factor to price those risk factors and the risk-free rate. And that gives me a different discount factor and then a different change of probability, and I can run the thing. To that, there is the argument of Cochrane, namely that, well, there is a zoo of possible risk factors, and you never know which one you can take. So the principle, what you get from those things is always the same. If is the same whether you work with the CAPM or whether you work with the stochastic, with the deterministic model, with the CAPM or the more generalized risk factors. If you plug them into a deterministic model, then you get implicitly a badly posed model. If you run the stochastic version of the thing, then the model becomes perfect in terms of monotonicity. Obviously, it's a stochastic problem, and you have to, in your scenarios, represent the risk factor, the evolution of the risk factors, so as to get the correlation between the revenue of each of the mu. You get it implicitly through the computation, which is, we get it free through the computation of the stochastic problem, the correlation of the mu with the risk factors. Well, the correlation is here, but okay, let's skip that. Then nonlinear discount factor. So the criticism of those things is that at the end of the day, you always calibrate the alpha, the stochastic discount factor, on the past. When you work with the deterministic model, not only you rely on the past correlation, but you imply to continue to use those correlations for the future evaluation of the plant. When you work in the stochastic risk factor version of the thing, you calibrate your stochastic discount factor on the past, but the correlation change when you run your stochastic problem. So that's an advantage. Well, the criticism has been that, well, we don't really know what's going to happen and in the future, so maybe calibrating those things on the past might not be good. Apparently, when one tries to introduce approximation of those nonlinear approximation of those linear discount factors, doesn't go too well. So then by nonlinear stochastic discount factor here, I mean that we resort to the risk functions that have to be calibrated again on the basis of the judgment of the user. But in the case of the risk function that we use, there are some people trying to look at some of the parameters that appear in those risk functions, not because they appear in those risk functions, but to try to relate them to forecasts that you can make on business cycles, and hence that's interesting. So, a reminder, the same as before. I have a model where I have the producer and the consumer problem, and I have there the risk function, the risk premium, and the risk-free rate in the investment problem. So the capital cost is compared to the value of the plant, evaluated the risk-free rate plus the value of the plant with the risk premium, the market clearing, and I have that generalized equation where the B of Z is destroying my monotonicity properties. We want to enrich the risk premium. So the way we do it, something that we started a long time ago, was to try to find the stochastic discount rate factor to get it from a risk function, because in fact formally it's just the same as a risk the derivative of a risk function. Then there are two different types of problems that you can consider, and we give different complexity of the problem. You can have the project finance approach, where you value each plant on the basis of its own merits, which is the way the problem was posed to us initially. And then at the end, initially people expanded, and then you concentrate again on the whole market, or at least on the pure market, and you finance them on balance sheet. Now, when you finance them on balance sheet, you look at the portfolio of your plants and possibly of financial product, and you need to value your product, taking into account the risk exposure that the company has, given the portfolio of asset that it has. So this leads to different to slightly different formulation, but the case study for which I have something is based on project finance, where the company invests in some particular project in one country and looks at the project on the basis of its own merit without considering its overall portfolio, which is not what they did before, obviously. Now, something is that you may have some information of risk factors that are priced by the market, and then you have the rest that definitely account for your risk and that you want to take into your problem. Well, we don't want to separate the two. We want to be able to mix the two. If there is something that is priced by the market, it should be in the model. If there is something that is not priced by the market, or that is priced by contracts that are internal to the sector but are not traded contracts, then they should be in the model. So this is the definition of the risk function. I think, well, it's a utility function with some properties, nice properties that give something, but it was developed by people in finance, and they are not very successful, so there is no need to elaborate on that, and no time to elaborate on that here. So in fact, there are two different formulations then. Whether you have a project finance, each plant is valued on the basis of its own performance, and you just look at the risk exposure of that plant, and that is the only risk that you want to consider. Now, if you think in terms of financing the plants on balance sheet, then you have to take the whole portfolio of the plant and see whether adding this plant or removing this plant is good given the overall portfolio. This is a different problem, but the formalism is the same. So we do, yeah. Yes, we take everyone that, well, most people who work with risk function work with CVAR. Since some time we like to work with the good deal, the so-called good deal measure, risk measure. The reason is that the so-called the good deal measure first was produced by people in finance, and also that it is based on parameters or things that are priced on the market for some of them, or that it separates clearly the idiosyncratic risk for those risks that are priced from the market. This is its formulation. You want to find a change of probability. So in contrast with the linear discount rate, the change of probability is not given. We want to find it. We want to find a change of probability, Q of omega, such that Q of omega is greater or equal to 0, but that's just to avoid arbitrage. But in fact, you need more than that. You need that it is strictly positive in order to get some equivalent probability in the sense of finance. So that means that when you change your probability, you don't drop some states of the world. If you think about that restriction, think of a stochastic program or a limit of stochastic program where at some stage at the limit you would have dropped some scenarios. Well, obviously you cannot find any continuity property between the problem before dropping those scenarios and the problem after you drop those. There's the same condition here. So we want that everything that has a positive probability in the initial problem keeps a probability. And then this thing, which is a constraint which relates the change of probability to what is called the Sharpe ratio, And the Sharpe ratio is a measure introduced a long time ago that measures the risk aversion of the market, and which is the expected return of the market divided by the volatility of the market. In that problem, the interest of that problem is that because people want to use the CAPM or like to use the CAPM, is that we can embed the CAPM into that formulation. We just have here those constraints that say that you have to price a few things. And if you want to use the CAPM, you say, I want to price the risk-free rate, and I want to price the market. You introduce those things here. If you want to price something else, well, you have more of them. And then what you have then is you are not only doing that, but you price those risk factors, and you have something else, which is the idiosyncratic risk, which is not priced by the market, but which is valued by the different agents. And so that good deal risk measure has the advantage of it mixes something that you want to do in the standard approach, the CAPM, and something that in fact you have in other risk measures, or that you have in general as soon as you want to deal with idiosyncratic risk. So you have a mix of both, and you can play of them. Also, something nice is that you can calibrate it either by the F if you by the value of the assets that are priced by the market, but you can also calibrate it by the Sharpe ratio, which is something that I think we take 0.7. I think for some time Warren Buffett's risk ratio was 0.7, but since doing less well these days, maybe it has changed. But in fact, you have some connection to the market, and an important one. Yeah. No. So far in the B of Z, we just took the linear discount factors, but the idea is that, at least that was mentioned in those NERA reports, is that it's important to take into account the possibility of hedging. In fact, in that B of Z, we can introduce a full model of hedging under one condition, namely that you do not have inequalities in that problem. And typically the kind of inequalities that I'm targeting here and that one often finds in some proposals, for instance, when you want to impose that a reliability option should be related to the capacity, the physical capacity, are those constraints that relate the position that you take in the financial market to the position that you have in the physical market. As soon as you have those inequalities, and if they are binding, then you destroy the usual properties that you get from finance. So under those conditions, namely that you have a full model of equilibrium of different assets that can serve for hedging, then you can show that the value of those assets, either you know them, that's the preceding the linear discount factor, or you don't know them, you have to find them. And then you can show that you find them by solving a nonlinear problem. So that means that you maximize for the different agents the position that they will take, taking into account their physical position here, xi, ui. They will take some position in the financial market, but you don't see them. They are implicit in the computation. So in fact, they get eliminated through some proof, let's say, taking into account that the fact that you price then the same thing as you'd price by each agent. So this is a nice property. In fact, you can have a full model that reduces a full model of hedging with variables for hedging. No constraint on those variables for hedging. Unbounded position, as in the financial theory. Unbounded possible. Well, no constraint on the position that you have on the financial assets, and the whole equilibrium then shrinks to some just optimization problem, and the outcome of the optimization problem are some Q and some mu, which is exactly what we had before in the B of z. So this is a B of z, which is more complicated in terms of deriving the B, deriving the probabilities, but which has exactly the same form. So that means that if you can solve, or if you have a software that solves the one with the CAPM, well, you have the same software that solves the one with those things, provided you write the financial model. So there is some application that Gauthier knows much more than I do on those things, which is based on Germany, where the Sharpe ratio is 0.7, but that's something that is in line with what you want. That may be a little bit, to show a little bit less risky version that there is on the market. Then two versions of the model, one with 11 scenarios, one with 88 scenarios. The thing was done by in a thesis of a master thesis, and different CO2 reduction. So in fact, you have if you have constraints, or if you have physical markets like on CO2 or like capacity market, they are in the model they are in the capacity expansion model, and you have financial assets, they are in the financial model, they are in the B of Z. So things like capacity market and CO2, they are in the A, and the others are in the B. Then different contracts, no risk trading, the no contract. All risk is trade complete market, then base load, seasonal, but in fact different things. System battery, renewable, wind, thermal, yeah. Then so we solve them by, we use proximal steps on, yeah. So that means that this is solved by a quadratic problem, and apparently updating those quadratic problems requires to reset them. So that takes a lot of time, which explains the 30 hours that we have for the larger model. But okay, given the type of expenses that those things mean, yeah. So you get this, let's say, the standard type of results, namely that if you have hedging, you can have more investment than if you don't have hedging. Well, that complies with the fact that uncertainty prevented investment. Now, this is a graph where things are expressed in terms of, let's say, standard financial metrics. You have the standard deviation, and you have the expected return, the thing that you have in the CAPM, the thing that you have in the risk. And this is the efficiency frontier. This is the efficiency frontier after hedging, and all the plans are all the investment are there. And these are the position of those plans into expected return, a standard deviation if we withdraw what it was due to hedging. Well, that one finds that one does investments after hedging that one could never have done without the hedging. So this is something that one expects and that can measure. Then one can also see one can also see what's the position of the plan with different type of contracts and without those contracts. So you have here different assumptions. So you have a capacity market or a baseload contract, a CO2 contract, a fully incomplete seasonal contract, in fact, whatever you want, not whatever you want, but okay, several things. And so you have some results for different things depending on the contracts. And here, the capacity market doesn't help really the renewable investment, but the future contracts written on the electricity price do. So that is something. So you work with one contract, you see where those plans are with other contracts, and when they are in the zone where you have high return and high variance, that means typically that people are reluctant to invest in them, and you try to have with the contract a move from that zone into those things where you come with more reasonable expected return and variance, or something which is easier it's easier to get financing. They're the same. The gas plants have a higher risk profile, and they are the most vulnerable ones in the market. But we know that. We also know that. Well, we compute with that when you introduce those contracts, well, you improve their situation, but still they are still facing a lot of risk. So in fact, everything can be, well, the analysis can be, yes, almost done. The analysis can be in more detailed, but in fact all the graphs can be put in those premium and variance framework that people in finance like. Okay, so this is essentially, well, those are additional elaboration. I will stop, no conclusion. Well, there's no need to conclude. In fact that, well, nothing to conclude. I don't have any conclusion. It's time, that's the conclusion.
So in the tradition of this workshop, we have a questioner, who's Jacob, who I hope is here. Yeah, okay, so here's a single question for you, I hope.
Single question? Can it be two parts?
Two parts.
So I thanks for that talk. So I think I want to return to the paradox of the multiple prices, and so I have one mathematical question, more kind of a practical question. So the mathematical part is an alternate explanation is you could say, so in this model everybody has the same pies. So the prices in the future, everybody has a shared understanding of what those will be. You could say an alternate explanation of the apparent difference in the present value is that they just have different views of the future value or the timings of those future flows. So that's the, I guess, more mathematical question. And then the more practical one is I hope you can expand on the reasons why there's not enough trading, or financial industry, or banks to step in and say.
Well, the first one on different views, that well, that's the question of ambiguity. Well, it would remain to be in. Well, an additional task would be to introduce those different agents with different views. In this stage, at least when we work with risk function, each one has the same view of the probability of events, but they have their set of probability functions that can be different. So the risk function can be different, and then they ultimately end up with different risk neutral probabilities which correspond to different views, but different views with the same set of scenarios. So they will put the same different probabilities on the same set of scenarios. I don't know whether one can write a model where people would consider that the future is fantastic and other people would consider that the future is awful, and would completely ignore the one who think that everything is great, would completely discount the view of the other. So I think we should keep that standard assumption of finance that they have the same set of scenarios. The introduction of the risk functions allows for differentiation of the views to the extent that after the treatment, after passing through the risk function, they end up with different probabilities for those stats. And I think after discussion with Georg Fluck that in at least some of the models of ambiguity in fact boil down to that. But it's very well possible that having different views on the future could lead to those things. Now, I would argue that we remain in the standard context. We do not invoke any esoteric theory, and we find those different prices just because of the basic formulation of the thing. So that's all I can say on the first question. What was the second one? Because I'm getting...
The second was, I hope you could expand on...
Well, the liquidity, well, we did work with liquidity, so, but not here, but in a preceding papers, where, I don't know, at least either we work with bid-ask spread exogenous, or we work with bounds on the extent of the trade that you can have. And in general, that drastically decreases the gain that you can have. Those things in general lead to very large trade, and if those trades do not materialize, then then you do not capture the bar. You cannot capture the gains. But okay, that is one can introduce the liquidity aspect, limited liquidity, either by bid-ask spread or by bounds on the trade. No, I think that would complicate the B of Z, and we did not do that here. We did that in other models, but where we did not refer to that separation of the A and the B. Yeah. So
we have time for maybe one or two questions from the floor. Maybe John Sheep.
Yeah. So if this is very nice. So my question is that you talk about the single agent problem when you derive that generalized equation formulation, and you talk about the problem being copositive and things like that. What about the multi-agent case? Do you still get the same copositivity property when you have a gain?
Oh, well, this is multi-agent. In fact, when
maybe I missed something. But then when you talk about the AZ plus B, is that for the single agent problem or the multi-agent problem?
AZ plus BZ is for the multi-agent problem. So the different agents differ by what they have in the B of Z, which is a different discount rate. We do not have any market power there. And the A of Z, you can interpret it as multi-agent or single agents, because we are in pure perfect competition. Ownership does not matter, but it matters in the B of Z. So we push the, let's say, non-monotone part of the multi-agent in the B of Z.
And you still have the B being copositive even in the
well, because we are working with risk premium. The risk premium by nature, it's a multiplication of a positive factor times a positive risk value, which is the mu. So we have copositive. But I don't know, we can derive something on that. Responding to a remark of Claudia 2 days ago, well, we prove unicity by the fact that all we have in B of Z is a continuous transformation, where the situation where there is nothing in B of Z, where we have perfect competition, and hence there is guaranteed to have a single solution, and hence we get the same property of odicity of results. So what we know that in some cases, even in that formulation, there is a single solution. And the question is to try to find whether we cannot find other cases where we have a single solution. But I'm personally more interested in multiplicity of solutions, because in general it signals something bad in the economy.
If I understand it properly, when you're looking at this good deal risk measure, the Sharpe ratio is an exogenous piece of information.
Oh yes, yes.
Is it possible to endogenize that, given that in the end it emerges from the market, right, and somehow have something that equilibrates with the Sharpe ratio?
I don't think it would be conceivable in the short future. So what is nice there is that there is some work on trying to relate values of, well, people in finance are trying to find some predictors of what is going to happen, or try to find relations between some evolution and the state of the business cycle. And there is some work now on those things, and in particular on relation with the Sharpe ratio and the state of the business cycle. Some people at the Stern School are doing that. But that does not endogenize anything at all. It's just a way of having information coming from the people looking at business cycles to get into, yeah. To endogenize, you need a model of the business cycle.
Yeah, I think we'll draw it to a close. Eve's not feeling very well, so I would congratulate on making it through to the end of the book.
Well, it was a little bit painful.